Okay, welcome everyone. I'm Alison from the Southern Cross Postgraduate Association. Here we are, part 3 of statistics and SPS with Dr. Megan Lee. So we're going into advanced 1 of statistics, and next week is our final session, which will be advanced 2 statistics and SPSS. So I'll put a couple of links in the chat box to become a member of the Postgraduate Association. And also just a little reminder that the association are running our Praxis conference in June on the Gold Coast campus. And we're open to receiving abstracts. There's a call for abstracts out. And we encourage students to present on any stage of their research, even if you haven't gathered any data just yet. We'd be interested in a literature review, whatever you'd like to present on your research. It's a collegial kind of friendly conference, and a great sort of way to practice presenting your research. So I'll put a link in the chat box about Praxis conference. Okay, that's enough from me. Thanks a lot, Megan.
Thank you so much, Alison. Welcome, everybody. Good morning. I'm Dr. Megan Lee. I am a senior teaching fellow at Bond University, but I did my PhD at Southern Cross University, which I finished in June of 2022. So I have a very deep understanding of what everybody is going through in their higher degree of research roles. I wanted to do a little bit of a shout out to the Southern Cross Postgraduate Association. I do this every time I do a workshop for them. I had a bit of a rough PhD in some ways, and the SCPA was really there to help support me and advocate for me. And I don't think I would have finished my PhD if it wasn't for the SCPA itself, the staff of the SCPA, and the friends that I made networking with the SCPA. So I would highly recommend joining the Southern Cross Postgraduate Association. They're not actually linked to the university themselves, so they're an individual independent entity. So if something does go terribly wrong, and I'm hoping that it doesn't for everybody, but if it does, they can be there to help support you. The Praxis conference is excellent. I enjoyed that. I presented at Praxis every year during my PhD. Even at the beginning, I presented my first Praxis 3 months into my PhD, and I just basically presented on what I wanted to do and what I kind of knew about the field at that point. And then my final Praxis, I wrapped it all up and I did my whole entire PhD in 15 minutes, which was a lot of fun at the end. So again, highly recommend the Southern Cross Postgraduate Association. If you are interested in following me on my socials or my website, you can. I do lots of things on diet and mental health, but it also gives you a bit of an idea of the progression from honours through to PhD and then getting an academic position. So you can follow that whole journey if you go back through my socials, because it's all there, because I began my social media, especially Instagram, during my honours year. Feel free to follow me. If you have any questions for me after today's advanced statistic workshop, feel free to email me. I welcome any and all correspondence and any help that you need. So what I'm going to do is in the chat box, I might get everybody to put in who you are, what degree you're doing, and if you're doing a higher degree of research, master's thesis or a PhD, what your topic is. And on a scale from 0 being no experience with SPSS and statistics to 10 being an expert in SPSS statistics, where you fall on that continuum between 0 and 10 in your expertise. Pop that into the chat box. We'll have a look. Marine ecology, Miranda, that's very interesting. Katarina's doing her honours in psychology. Yes, so the workshop will be very helpful for honours students as well. particularly today, we're looking at regression, and regression is usually the statistical analysis that is used during an honours thesis, looking at predicting relationships in surveys. Risha's doing a PhD in business and tourism in marine protected areas. And there's about a 4 on the level of expertise in statistics. PhD in psychology, goal setting for Grace. Alan, Masters of Teaching, coursework, practical experience with SPSS. Ooh, and R, Python. Very, very cool. I'm currently learning R. It's very, very fun, kind of. You have to learn computer programming. So SPSS, which we're running today, is all clicking, which is a little bit easier. So Alan's coming in with a little bit of expertise. Lisa, studying PhD, looking at midwife's personal experiences of birth trauma, returning to the workplace. That's amazing. Miranda, 5 in stats and R Studio, no experience in SPSS besides these workshops. So that's a really good point that Miranda brings up. If you don't have any expertise in SPSS, it may be wise to go back to the first workshop that we did on beginner statistics in SPSS, where we go from the very basics and the foundations of taking your data outside of your survey or your experiment, putting it into SPSS, how to clean it, what all the tabs mean, what all the buttons in SPSS means, and then our intermediate statistics workshop, which was 2 weeks ago, where we looked at the basics of correlations, relationships, and between group differences if you've got 2 groups. So if you need a bit of a refresher, go back and have a look at those 2. Now, this advanced statistics workshop and the other statistic workshops that we have done are designed specifically in a way that during the workshop you get the foundational knowledge of statistics and how to use SPSS, and then you use the recordings, which Alison will pop into the chat box and we'll send out to you once we have this recording ready. You use the recording so you can use it while you're doing your own data, and you can rewind, you can fast forward the boring bits, you can pause, you can go back. And so that's why these workshops are designed like this and recorded in that way, so that when you are doing your own live statistics, you can follow along the steps that we are doing. Lisa asks, are we covering moderators and mediators? Yes, next week. On Thursday of next week, we will be doing logistic regression, ANOVA, and mediation. Mediation is just a small tack on to what we are doing today. So once you've looked at correlations from the last workshop, it builds into the regressions, which we're doing today, which then builds again into mediation. So it's kind of this step-by-step process. And once you understand those things, you will understand the next set of instructions, which is great. Now, SPSS itself is not the best software program for mediation. It's clunky. You have to put in, or you have to add on a add-in, and it's not very user-friendly when it comes to mediation and moderation. So I'm going to show you next week another software program called JASP, which is free, online, doesn't cost anything, and it's one of the best ways to do mediation, apart from looking at R and those other, and Stata and those other programming softwares. JASP, yes, JASP. And I'll also show you how to download it and things like that in the next workshop, so you can play along as we go. Right, so let's get going. Are there any questions that you have for me before we start? Okay, cool. So today we are going to go step by step through the steps of completing a regression analysis. We are going to start by looking at correlations, which we did last time, but we do need to touch on this again, because the very first step in a regression analysis is ensuring that you have significant relationships between your variables. So you need to do this by having a look at correlations. Then we will move into simple linear regression when you want to predict an outcome from what is known about one predictor. And the outcome and the predictor that we will be working with today is diet and depression, because this is the research that I do. It's what I did in my PhD. It's what I know best. So the outcome variable is depression, because that is what we are looking to see the outcome in. And the predictor is diet quality. So if we change diet quality, then what will happen to our depressive symptoms? Then we will move on to multiple linear regression. When you have more than one predictor, so say we wanted to find out what the depressive symptom outcome is when we're looking at diet quality and BMI, because BMI has a high relationship between diet quality and it also has a relationship with depressive symptoms. So if we add BMI and we wish to control for BMI, does diet quality still predict depressive symptoms if we are also controlling for height and weight? And then we will talk about hierarchical multiple linear regression. And this is kind of the final step in regression, when you wish to control for covariant factors and you know from the literature what order those factors fall in. And that's the most common regression that we use. So we'll go through all of those today. So firstly, and Alison, can you keep an eye on the chat box, because I can't see it. If anyone has a question, could you just call it out to me? Thank you. So correlations are the relationship between two variables. And as I said, we talked about this in detail in the last workshop. So if you would like to go back and have a refresher of that, feel free to do so. But they are very, very important for regression. You cannot do a regression with non-significant variables. So if there's no relationship between two variables, then obviously you can't predict the relationship between the two variables. So it's really, really important to run your correlations first. And when you run your correlation analysis, it also helps with your assumptions testing. So the assumptions that we talked about last week that are very common: normality, whether your variables are normally distributed; linearity, whether they fall in a straight line; and independence, that each of the people who are in your survey or you're in your experiment do not influence each other's answers, and one person hasn't done the survey twice or hasn't been in the intervention group twice.
There is a
basically.
question there in the chat box, Megan, sorry. It's from Katerina. Can we use different levels of depression for simple linear regression, or should it be different variables?
Very, very good question. So everything that we are looking at today will be on continuous variables. So when depression is measured on a continuum from, like, say, 0 to 60, and when diet quality is measured between, say, 0 and 105. If you go back to the first workshop, we looked at how do we take our, say, 20-item Likert scale questions from depression and turn them into a continuous score for each participant. So that's a very, very important step in doing these analyses. So correlations and regression are always done when you have continuous variables. When you want to look at depression, say, in levels, so if you took a depression score and you said 16 is the cutoff, people underneath 16, the score of 16, don't have depressive symptoms, people above the score of 16 do have depressive symptoms, then that's a different analysis. And we'll go into that next week. Logistic regression, when your dependent variable or the depressive symptoms score is dichotomized like that, so does or does not have depression. And then ANOVAs, when you have different levels of depression. Say you've got no depression, mild depression, moderate depression, and then high rates of depression. If you split your participants into those 4 categories, you would then run an ANOVA. And that's what we will be doing in the workshops next week. So everything that we're talking about today is when your variables are on a continuum from negative infinity through 0 to positive infinity. So that's very, very important. And you can't do regressions on when your predictor and your outcome variable are not continuous. They turn into a different analysis. So correlations themselves tell us the relationship between two variables. Excuse me. They also tell us the strength and the direction of that relationship. So in our first box here, we have a positive correlation. So say we use the example of diet quality and depression again. Each of the dots on this scatter plot is one participant's score on diet and depression and where they meet. If our dots are trending in an upwards fashion from the bottom left to the top right-hand corner of the scatter plot, that is a positive relationship. And what that means is as diet quality goes up, depressive symptoms go up. So if we saw a positive relationship like this, that would mean that as people got healthier, their depression got worse. So we wouldn't be hypothesizing that, but we could see that. And the strength of the relationship here is 0.4. So all correlations run between -1 through to 0 up to +1. The closer to 1, negative or +1, the stronger the relationship. And the closer to 0, the weaker the relationship. So 0.4 is about a moderate strength relationship. In the middle here, we can see a scatter plot of a correlation with no or very weak, a very weak or no correlation or relationship. As you can see, all the dots are all scattered around in a cloud. They don't trend in a certain direction. And the line of best fit in the middle is horizontal. That means there is no relationship between diet and depressive symptoms, basically. And you would report that. But then if you saw this, you would not then move on to a regression because there's no relationship to predict. Then here on the right-hand side, we have our negative relationship. It's trending from the left-hand corner down to the right corner. The dots are trending downwards. And again, our R statistic is -0.4. A negative relationship would mean that as diet quality goes up, depressive symptoms go down. That's the relationship that I would hypothesize that we would see, and you would assume that the R would have a negative symbol in front of it. So that's 101 correlations. The scatter plot is really, really important. These scatter plots here are a really important part of correlations because not only do they tell us the strength and the size of the relationship and the direction of the relationship, but they also tell us whether or not we can fit a linear line through the scatter plot. So our assumption of linearity is also found in our correlation. All of these scatter plots are linear, which means you could put a straight line through them. If you're starting to see the dots form a W or a U or some form of curved relationship, that is not linear, and then you cannot move on. Your assumption of linearity is not met. So graphing your data is really, really important, and I'll show you how to do that in a second. So correlation is the little brother of regression, and regression is the big sister. So regression is just an add-on to correlations. So not only does it tell us whether there is a relationship, but it can tell us what we can predict from that relationship. And this is the regression formula. Y hat, which is the predicted value of your outcome. So if we look at Y is going to be depressive symptoms, our outcome. So we're trying to find the predicted outcome of depressive symptoms. And to do that, we use this formula. So y hat equals B1 X1 plus BO. B1 is the slope of the regression line, or the amount of difference in depressive symptoms associated with a 1 unit difference in diet quality. X, I is the value of the predictor variable, so the value of diet quality, and BO is the intercept. And that is the predicted value of Y when there is no diet quality, so 0 diet quality. Now, to make more sense out of that, here is our regression scatter plot with 6 participants. So Y hat, so we're always looking for the outcome of Y, or the predicted outcome of Y from the formula. So here we can see this is body weight. So Y, we're trying to find out how heavy somebody is from their height. Each of these stars on the scatter plot is one participant's height and weight intersecting. So this participant here, this star here, their weight is around 120 pounds and their height is around 50 inches. This participant here, this star here, their weight is around 165 pounds and around 78 to 79 inches is their height. This line in the middle here, or our regression line, or the line of best fit, is the perfect model. And how far each of the stars are away from the line is our error, or our residuals. So we're never going to have the perfect model or the best model. The best model is always around the average, right? So the mean. So we were always going to have a little bit of error between each participant and the perfect model. And these little bits here between the line and the star is that error or that residual. Now, residuals are really important in regression because all of our assumptions that we do before we run our model are based on these residuals, or the error between the best model and the model that we have. So here we have Y, or body weight, equals BI, or A, plus B1 X1. So going back to our formula, A is the value of weight when there is no height, or 0 height. So here everyone starts with a baseline of 80. And this is just for this model. Plus B1 X1. So whatever the person's height is times the slope of the line. Now, don't worry too much about the semantics behind the formula. One of the things that we can do once we have run our regression in SPSS is we can pop our value of X for each participant into the formula. We can pop in what our slope comes out as and what our intercept comes out as, and we can predict somebody's depressive symptoms from their diet quality. And this is the whole premise of regression, being able to take the value of somebody's predictor to find out what their outcome would be. All right, any questions before we move on to the assumptions checking? Can I please double down? Is it right that regressions are used to predict relationships between variables? Yes, they are, Katerina. Therefore, poor diet predicts higher depression. Yep, that's exactly right. Or height would predict weight as well in that other example. All right, so who can tell me what what assumptions are, what do we use assumptions for? Why are they important from our last two workshops?
Sorry, just off the top of my head, if the assumptions aren't valid, then you can't rely on the results of the, say, regression, whatever the analysis is.
Exactly, Alan. Thank you very much. That is exactly right. Assumptions are things that need to be met before we can do our analysis. If the assumptions are not met, then our results may be flawed. And you have to do them. If your assumptions aren't met, there are things that we can do to our data to mitigate the risk of the results being wrong, like transformations. We can bootstrap things like that, and I'll show you that a little later. So the assumptions for regression. Regression has the most assumptions out of all of our data analysis. So apart from the usual normality, linearity, and independence, there are a couple more. So we'll run through them really quickly. Independence, once again, this is met in your study design. As long as you ensure that your participants aren't in more than one group, unless you're doing a paired samples test where they should be in two groups, like pre and post test. But if they are independent, they should not influence each other's answers. They shouldn't do the survey twice. They shouldn't be the same experiment twice, things like that. So making sure independence is met in the study design. Reasonable ratio of cases. So N, which is our sample size, and our predictors, which is K. Now, there used to be really complex formulas that we used to ensure that we had a reasonable ratio of cases to predictors. But now we use what's called G-power. I think I have a slide. Yes, this is our G-power sample calculation. Now, what I'm going to do is I'm just quickly going to put into the chat box the G-power download website. So if you don't have it already, you can download it. So what G-power is, it is a calculator that tells you what your sample size should be for the analysis that you're doing with the power and the probability that you would like. So in this example in the slide, we would like to look for a medium effect size of 0.15 with a p-value or a significance error level of 0.05, power at 0.95. I usually use a power of 0.80 because that's more medium. And then you put in how many predictors do you have in your in your analysis, and then the total number of predictors, and it will spit out how many participants you should have or you should collect. Now, G-power should be done prior to recruitment, prior to data collection, and they usually ask you to report your G-power sample size in your ethics application now and any research proposal that you do. So over here where it says total sample size, that is where it tells you how many participants you will need to make power. Now, we always overshoot the G-power sample size by 50 to 100 participants because you will and can lose participants in your data cleaning. People who don't meet the inclusion or exclusion criteria, people who are who haven't completed your outcome and your predictor variables, things like that. So we overshoot that. But as long as we are over that sample size of 119 in this case, then your N to K ratio is met. And that's really important for all analyses, not just regression. Our next one is normality. So we want to see normality of our predictor and our outcome using histograms, QQ plots, and Shapiro-Wilks. We are also interested in outliers, and outliers you can find in box and whisker plots. If you've got outliers in regression, They are important, but they're more important if the outliers are on 2 variables rather than 1, like a normal analysis. We want to see if we have that linear relationship between the 2 variables with a straight line in the scatter plot. We want to see normality, linearity, and homoscedasticity of our residuals, not between the 2 variables as required in correlations. Then we have independent errors, which is done using the Durbin-Watson. This is inside the regression analysis, and I'll show you that. And reasonable ratio of cases. I've done it twice because it's so important. Right. So last week we analyzed correlations, and we are now going to expand on these analyses by taking them a step further into predicting relationships using regression. Now, regression I find is my favorite analyses because it gives you the ability to look at the prediction between 2 variables, but you can also control for all the other variables that could be influencing your outcome. So who here can tell me, right in the chat box, what are some other variables or co-varying factors that could influence depression that aren't diet quality? Matt's saying here, I used a convenience sample. So using power can give a retrospective look at the N and K. I used a variation of this from SurveyMonkey that had a power calculation. Yep, that's absolutely right. You can do it that way as well, using a convenience sample and going backwards. So Miranda, age and gender, yes. So being older or being younger could influence depressive symptoms. Females and males may have differing levels of depressive symptoms, so that might be an influence. Health status, what sort of health status, Matt, do you think we could control for? So do you mean BMI?
Probably more things like a walk test, some of those standardized tests, step test type of thing.
Yeah, cool. Yeah.
What's your fitness capacity type of thing?
Yeah, cool. So physical activity levels, things like that. Environment, family, housing. Yep, absolutely. Good. And the other lifestyle factors like sunlight exposure, sleep quality, medication is a good one. All these things that could be influencing depression. Excellent. So today we are going to be able to do that. Now, in these workshops, I use a live data set that I recruited last year in March called the Vegetarian for Life data set. So this data set, we basically were looking at participants who have been vegetarians for their entire life for reasons like culture, religion, and upbringing, and who have never eaten meat. And we wanted to see what their depressive symptoms were. And we also wanted to measure their diet quality and see if there was a relationship between those 2 things. But we also wanted to control for those things that we just said, like BMI, physical activity, sleep quality, social connection, things like that. So our research question for today is, does diet quality predict depressive symptoms after controlling for other demographic and lifestyle factors? So we're not going to look into things like past childhood trauma and things like that, which are also highly relative to depressive symptoms. We're mostly looking at demographic factors and lifestyle factors. And the best way to answer this research question is through a survey. So we asked our participants to tell us a little bit about themselves: age, gender, marital status, geographical location. We asked them to complete the 20-item Center of Epidemiological Studies for Depression scale. We also got them to do 27 questions on their diet quality, and we asked them their lifestyle factors like sleep and whether they were physically active, things like that. But before we get into our regression, I wanted to show everybody a little tip and trick for getting your output in SPSS to come up in APA 7 format. So you don't have to do it yourself. And once you do this once, it will automatically do APA 7 formatting every time you do your analyses. So I'm going to stop share here and I'm going to bring up SPSS. I'm going to share my SPSS so I can show you how to do this. So here is SPSS. Can everybody see that? Yep, good. So we want to go to, just checking, edit and options. Edit, options, and then you want to go to the tabs across the top. Can you see this? Tabs. Where it says pivot tables. You want to click on APA times Roman 12-point font. There's also APA sans serif if you prefer that. So you click on APA 7 times 12 font, apply, and then OK. And now from now on, every time you produce output in SPSS, it'll be in APA 7 and you can copy and paste it directly into your assessment task, your honours thesis, or your PhD, and it should be perfectly done in APA 7.
Could you just run through that one more time? I was rapidly trying to open my SPS.
Yeah, yeah, absolutely. So it's edit, options, pivot tables, up the top here in the bars up the top. And then APA times Roman in this box here. And then apply. And OK. Thanks, Hasini. Very good.
Right, thank you.
Thank you. Right. So that's a little tip. So now let's move into our regression in SPSS. So what we're going to do is we are going to first start with correlations because you can't run a regression without significant variables. So we must first see if our predictor and our outcome variable are significant and which of our demographic and our lifestyle factors that we measured in our survey are also significant with depressive symptoms. Then we are going to move on to multiple and hierarchical regression, where you are controlling for these variables. And we know the order from the literature about what order these variables are of importance in your model. And I'll tell you a little bit about building models and the best ways to do them. Right, but first, you must always have a significant correlation between your variables to conduct a regression analysis. If your relationships between your variables are non-significant, you must stop. You cannot proceed. So we are going to run our correlations first. So back to SPSS. Right. In SPSS here, we have our data view with all of our variables across the top: gender, age, BMI, geographical location, marital status, education level, whether or not our participants were vegan or vegetarian, what type of vegan or vegetarian diet that they self-reported as, what their sunlight exposure was, what their total score on the depressive symptom scale was. So we took all 20 questions and turned them into a total score for each participant from 0 to 60, with higher scores equaling greater depressive symptoms. We also have a variable here, which we will be using next week when we run logistic regression. And the variable is split between no depressive symptoms and experiencing depressive symptoms. So we've basically taken our total depression score, and the cutoff score is 16. Anyone below 16 is categorized as not having depressive symptoms, and anyone over 16 is categorized as having depressive symptoms. Then we have our dietary quality score, so DST, the dietary screening tool score, and it's a total score between 0 and 105. Greater scores or higher scores mean greater diet quality or higher diet quality. Then we've got social connectedness score and a sleep quality score. And then we've also got the DAS down here, which we're not going to use today. We've got height and weight, which we used and transformed into BMI. And then we have our questions for the depression scores and things like that. So we're going to basically be using these ones up the front here. So that's the columns, and in the rows is each participant's answer on each of these variables. So the first participant is a male. He's 29 years old. His BMI is 22.13. He lives in Australia. He's married. He has a postgraduate level of education. He's a vegan. His sunlight exposure is more than 3 hours a week. His depression score is 10, which is under that cutoff of 16. So he's categorized as not having depressive symptoms. And his diet quality score is 78 out of 105. So you can go through. We have how many participants? Scroll all the way down to the bottom. We have 319 participants in our survey. After we cleaned the data, we lost about 100. On the variable view tab, again, you can see all the variables that I mentioned, and then the label here will tell you what they mean. Inside the label, on my total scores in particular, I like to label them with their full name of the scale, the acronym for the scale, what the scores range between, and what the higher scores mean, so that when I'm interpreting my data, particularly in regression, I kind of know what's going on. So I've done it also for the dietary screening tool and the social connectedness scale. And you'll see later on when we go through our interpretations of the data, you can directly see what they mean from those labels. If you want more of an explanation of the variable view and what all of these columns mean, go back to the first workshop. The most important thing is to make sure that your categorical variables are categorized by number, so SPSS can tell what they are. So in gender, we have males equaling 1, females equaling 2, transgender 3, non-binary 4, and people who prefer not to answer as 5. And making sure that your measures are correct. So all our categorical variables are nominal. Our continuous variables are scale, and you can see the ruler there like a continuum. And then our ordinal variables, which are variables that are in an order, are also correctly labeled, because SPSS doesn't always get it right. And if these are labeled incorrectly, your results or your analysis won't work. Any questions about the layout of SPSS before we get into the actual the beginning of our regression? All good. Okay. So the first step in a regression is to do a correlations, and at the same time, in our correlations, it'll tell us something about our assumptions testing. And we're just doing this on the predictor and the outcome variables. So it doesn't really matter for the other variables. And you'll see we've got some covariates here, like our demographic variables that are categorical. So we can put them into our regression model as well if we choose. So to run a correlation, the first thing that we kind of want to do is to have a look at a scatter plot of the data. So we go into graphs, scatter and dot, simple scatter, define. And then here in the box, the variables are all labeled with their label name. I tend to like to right click and display the variable names because they're smaller and I understand them better. So our Y variable is our outcome variable. So who can tell me what the outcome variable is in our question?
Is it depression or level of depression?
Very good. So depression, and the way that we measure depression is with the Center of Epidemiological Studies of Depression total variable. So we put the CESD total into the y-axis box. And then what is our predictor variable? In our question. What is our predictor variable? What are we using to predict depressive symptoms? Nutrition or diet quality? Very good. And the way that we measure dietary quality was using the dietary screening tool. So the dietary screening tool total will go into the x-axis on our scatter plot. And then we just want to click OK. And then I have to stop share and reshare my output, which is just taking a little bit of time. And you'll see down the bottom, if you think SPSS has stopped, down here is a little note saying that it's running the graph. So as long as it's saying that, it's still thinking.
There's a quick question from Alan there. Is the data from your actual study?
It is. It's live data from our actual study on vegans and vegetarians for life that we did in March of last year. It's currently under review. Yeah, which is really interesting. So I'm resharing my output screen. And here is our scatter plot. Can everybody see our scatter plot?
Yeah.
So our scatter plot tells us some really interesting things. It tells us, firstly, what the relationship looks like. So remember when we're looking at those scatter plots at the beginning? And who can tell me what way these dots seem to be trending? Are they trending from the bottom left to the top right or from the top left to the bottom right?
I see no trend.
You
That's a
see no
cloud.
trend. That's
Yep.
interesting. So because it's very subjective, we can get SPSS to tell us if there is a trend. So if you double click on the graph, it will bring up a little chart editor. And in the chart editor, you can add a fit line at the total. So we'll add the fit line and see what SPSS tells us about whether or not there is a trend. What do we think now? Matt's got it. So there seems to be a negative trend. The dots are trending negatively. Now, you're not completely wrong that it looks like there is no trend because they kind of are in a cloud. So we might have here a weak relationship. So this is already telling us something about our prediction of our relationship and the strength of the relationship. Now, another thing that the scatter plot tells us is the assumption of linearity. Can we put a straight line through this scatter plot? Yes or no? Yes, Katarina, we can. And SPSS has put that line of best fit through. If you saw the docs looking like a W or in a U shape, then there would be no linear relationship and you would not be able to move forward with a correlation or a regression. So we kind of see this negative relationship. So what does that tell us about the relationship between diet quality and depressive symptoms? If we were to interpret this using the scatter plot.
So your depressive symptom score decreases with, I'm guessing a higher dietary score is higher quality diet.
Yep.
So eating better may
Yep.
improve your depressive symptoms.
Very good.
Become less negative.
It is very good. So as diet quality goes up, depressive symptoms goes down. Good. Now, we have already said there might be a weak or a moderate correlation, but we can't really see that just from the dots. We do have our R squared up the top there, but we won't go into that just yet because one of the things about this is that this is all descriptive, right? These are descriptive statistics. It shows us that there could be a relationship. It shows us that there could be a negative and a weak relationship, but it doesn't tell us whether or not this is significant. So to do that, we need to run our correlation analysis to see if this relationship that we are observing in the scatter plot is significant or not. So let's do that, shall we? So we'll go back to our sharing our SPSS and we will run our correlation to see if that relationship is significant and we can move on to running a regression. So we'll go to analyze, correlate, and bivariate means two variables. You can also do confidence intervals. We're not really interested in that at the moment because we're not going to report the correlation. We're just using it to see if there is a relationship. And here we have our correlation box. Now, what I'm going to do is I'm going to kind of throw everything into the correlation. I do want to see whether there's a relationship between diet quality and depressive symptoms, but I also kind of want to see later on for our regression, for our multiple hierarchical regression, what other variables that we were interested in also have a relationship with depression. So whenever I do a correlation, I always put the outcome variable first. So display those variable names. In it goes. And then the predictor second. This is just, you don't have to do this, but this is for ease of interpretation. It makes it easy once you get your correlation figure to interpret what you're seeing. And then you want to put your variables in like, let's do our continuous variables first. So age, BMI, because there's a relationship between diet and depression with BMI. Then social connectedness. So whether or not how socially connected we are is influencing diet and depression. And then sleep quality. Then we'll put our categorical variables in: gender, geographical location, marital status, education level, and sunlight exposure. They're all the variables of interest. Now we'll click here on Pearson's correlation for our two continuous variables, so all of our continuous variables, but you also want to click on Spearman's correlation because Spearman's is a better correlation to use for those categorical variables at the bottom there. So you want to be interpreting them correctly, and Spearman's just adjusts for the fact that they're categorical and a continuous variable. And then you click OK. And then I'm going to have to share my output again. Now, don't panic. Look at all those numbers. This can be quite overwhelming when you first look at a correlation matrix, but all we're interested in this line of numbers is the very first column. So your Center for Epidemiological Studies of Depression scale, and you can see here that my label has attached to the table, which is really good because it helps with my interpretation. So all we care about is this first column. We're not looking at all these other numbers over here, therefore later. So our Center for Epidemiological Studies of Depression scale, let's have a look at dietary screening. So our diet quality score here, and this is why I put them in the order that they're in. So who can tell me what the correlation is between diet quality and depressive symptoms? Pop it into the chat. It is negative. What's the correlation? So the correlation coefficient here is our R value. What is it? How would we report it? Weak to moderate? Yeah, so it's negative 0.33. So that's telling us a similar thing to the scatter plot. Number one, we have a negative relationship. As diet quality goes up, depressive symptoms goes down. It also tells us that we have a moderate relationship. So for R, or Pearson's correlation, the relationships, anything around 0.2 or less is weak, 0.3 to 0.4 is moderate, and anything greater than 0.5 is a strong relationship. Now, underneath our correlation coefficients, that's our R, is our p-value or our significance value. What is our p-value? Pop it in the chat box. What is our p-value? Very significant? Well, there is either significant or not significant. It's a bit of a argument in statistics about very significant. Not significant. No, it's not. It is significant. So is it greater than 0.05 or less than 0.05? It's less than 0.05, which means that it is significant. So although we've got a weak relationship or a moderate to weak relationship, it is a significant relationship. So there is a relationship between diet and depressive symptoms. Now, all we care about for the rest of this column is which of the other variables are significant with depressive symptoms. Any variable that is not significant with depressive symptoms cannot go into our regression later on. So who can tell me here, going down the first column, the Center of Epidemiological Studies column, which variables are significant? So which variables are under 0.05 significance and therefore will be included in our regression? Social connection, yep. Social connectedness. Does anyone want to interpret the social connectedness R value? And this is something that happens every time I do these surveys. Every time. Sleep quality is significant. What else? Yeah, Alan. So the more socially connected people are, the lower their depressive symptoms. But have a look at the strength of that relationship. So social connection, always, whenever I do any of these surveys, and I always do the surveys with the same variables because of the replication crisis, so that I'm always replicating the same thing. Social connectedness is always the strongest predictor in depressive symptoms every time. Very, very interesting. And part of the Vegetarian for Life research that we're doing is around that social connection as well. Right. What else is significant and we're going to put into our regression later on? Social connection, social connectedness, sleep quality. What else? Sunlight exposure. Yep. And what about our demographic variables? Marital status. Yep. And education. Excellent. Very good. Now, the rest of the correlation matrix isn't really that important. However, for the assumption of multicollinearity, which means we don't want any of our predictors to be too closely related to each other, we just want to go through and check that the R values of all of the other variables aren't around 0.9 or 0.8. And by having a quick look through the R values of the rest of them, everything seems to be non-collinear. But there is another variable or another way we check that inside the regression analysis as well. But a quick look across the R values between the predictors shows that there's not really any that are too closely related to each other. Good. So now we're kind of forming a little bit of a plan for our regression. I'm going to let you have a 5-minute break now till 10:38, 10:40, and then we'll come back and we will run our regressions.
Okay, thanks, Megan. Are you able just to pause the recording while we're on our break?
Yes, I can.
Thank you.
Is everybody back? Yep. Nice. Okay. So now we're going to move on to our actual regression analysis. We'll run through simple linear regression first when we're only interested in the relationship or predicting the relationship between our predictor and our outcome. And then we'll move on to multiple and hierarchical regression when we want to control for other variables and we know kind of what order those variables should go into the model. And we'll talk a little bit about regression modeling, which is really, really important. So we've done our correlations. We've found that there is a relationship between diet quality and depressive symptoms. And we've also found that there are relationships between several of our demographic variables and our lifestyle factors and depressive symptoms as well. And we can build them into our regression. So the next step is ensuring that our assumptions are met. Now, our assumption of independence, we have met through our research design. So we ensured that no one person did the survey more than once, that people didn't influence each other's answers, things like that. So that's all done. We've also ensured that linearity has been met when we did our scatter plot earlier. So we know that there is a straight linear relationship between our predictor and our outcome, and that there's no strange U-shaped or non-linear relationship. Now we move to normality. So normality is an interesting one in regression because usually in analyses, we want our outcome and our predictor variable to have a normal distribution. And we want to check that there are no outliers or no people who are way different from the rest of the pack. This is not as important in regression as it is in other analyses because, number one, we should have met our assumption of reasonable ratio of cases and sample size using G-power when we were collecting our data. We should have enough of a sample size that normality should be met using the central limit theorem. So that should not be too much of a problem. If we've met that sample size with G-power, normality should be pretty good. And outliers in regression on each single variable are not as important as outliers across the two variables together. So those assumptions are actually within the regression analysis itself. Now we can go and do histograms and QQ plots and box plots and Shapiro-Wilks and check our normality and our outliers, but it's not as useful as looking at the outliers amongst the residuals and the normality amongst the residuals. So we'll do that instead. Now, this is a really important point that I want to get to, is that the depression variable should not have a normal distribution. If you had a normal distribution on a depression scale, there would be something very wrong with your participants, because depression should be positively skewed down the end of no depressive symptoms, with more people in that area that don't have depressive symptoms than people who do. If you see a normal distribution in a depression scale, then something's very wrong. So you don't want it to be normally distributed anyway. So let's move on. We won't worry about our assumptions testing for normality and outliers because we'll do it inside of our regression analysis. We've done our assumption of linearity and made sure. So now our normality, linearity, and homoscedasticity of our residuals is important, or our errors, and multicollinearity, which we already had a bit of a look at in our correlation matrix when we looked at all the values of R across the predictors and just made sure that no two predictors were too closely related. Now, if we had to put the depression scale from the DAS that we did have in our survey into our correlation matrix, it more than likely would have been highly correlated with the CESD scale, or the depression scale, the Center of Epidemiological Depression scale, because they're measuring the same thing. So we are not going to put the DAS in, and you will not put variables in that are too closely related to any of the other variables. If you run a correlation matrix, you find a variable or two variables that are closely related and have an R value over 0.9, one of them should be removed. You shouldn't be doing a regression with collinear variables. Right, so let's run our simple linear regression. So the first thing that we're going to do is we're going to run our regression with just our outcome and our predictor, not controlling for any other variables, just seeing what the relationship is between diet quality and depressive symptoms. So to do that, can everybody see SPSS before I move forward? No, I haven't shared it. Now can you see it?
Yes, it's there.
Perfect. Right. So we go to analyze, regression, linear, because we've made sure that we have a linear relationship. Our dependent variable, or our outcome variable, is the CESD total, just like in our correlation. And our independent variable, or our predictor variable, is diet quality. Good. Then in our statistics box, we would like to see our descriptives, so that will tell us the descriptives. We don't need collinearity diagnostics because we don't have more than one predictor. We don't need to see our R-squared change because we don't have more than one model. We could look at our confidence intervals. Durbin-Watson, which is our It's our measure of independence within the regression. And continue. Plots, we can do our residuals and our predicted values. Oops, they didn't go in. So a little plot of our residuals, and this will be our assumptions testing of normality and heteroscedasticity of our residuals. And you can do some histograms and normal plots of the residuals. So that's our assumptions testing. Right, and then click OK. Then I will take you over to the output screen and we'll run through our simple linear regression with one outcome and one predictor. So our first box is our descriptive statistics telling us the mean and standard deviation of depression and diet quality. So this does give us a little bit of information about our data. So here it tells us the mean of depression is 14.28. Who remembers what the cutoff score was for depression that I mentioned earlier? So the cutoff was 16, very good. So the descriptive statistics tell us here that overall, on average, our vegetarian for life population is under that 16 cutoff score. So we have a population that on average is not experiencing depressive symptoms. Now, this has the potential to impact the way we would interpret our results later in our discussion, because we have a population that's not really experiencing depressive symptoms. And then the dietary screening tool is 64. The scores range between 0 and 105, with higher scores equaling greater diet quality. So 64 is quite high for the dietary screening tool, which is good. And that tells us a little bit about our population again, that they have a high diet quality. But we're not comparing them to anyone, so that doesn't tell us anything about them compared to the general population. Then SPSS will give us the correlations. We've already seen them earlier between the two variables, so we don't need to look at them again. The variables entered or removed box tells us what our model looks like. Now, this is not that important when you're with one predictor and one outcome, but later on when we do our hierarchical regression, that becomes really important because we can check that we've done our modeling correctly. The first most important box is our model summary. This box tells us our R value. So big R, so little r was our correlation value. Big R is our regression value. So our big R here tells us that our regression value is 0.275. And so this is our coefficient of determination. And it tells us a very important thing about our relationship between diet quality and our depressive symptoms. So it tells us that the relationship is, and it is interpreted the same way as little r, weak to moderate, a weak to moderate relationship because it's around 0.2. Then our R squared, that's our coefficient of determination, sorry, not R. R squared tells us kind of the percentage of the variability in depressive symptoms that is taken up by diet quality. So we take R squared and times it by 100 to make a percentage. What percent of depressive symptoms is taken up by diet quality? %7.6%. Excellent. Which means that 93 to 94% of depressive symptoms is taken up by other things other than diet quality. So this is a really, really important value, this R squared. We also look here at our Durbin-Watson. This is our assumption of independence of residuals. We want Durbin-Watson to be greater than 1 and less than no, we don't want it to be less than 1 or greater than 3. So here we might have a little bit of a problem with Durbin Watson. I'm just going to check that. I think it's between 1 and 3. I'll just make sure. I always get this around the wrong way. Check my assumptions. Yeah, values under 1 or greater than 3 are a cause for concern. So anything between 1 and 3 is what we're looking for. So here we kind of may have a problem because our Durbin Watson is 0.63. So we may need to bootstrap our sample. Now the ANOVA box. This box tells us whether our model is significant. So who here can tell me whether the model of diet quality and depressive symptoms is significant or not? What is the p-value here?
It's
Significant?
It's significant, but it's not stated, is it?
Yeah. Right at the back of the ANOVA box is our sig value.
Yeah, but it's less than,
0.00.
but yeah, it doesn't tell you what the actual number is. Okay.
Yes, so it does tell us what the number is. So F next to the significance is our regression value.
Yeah.
25.988, but that won't make any sense because it's not compared to anything. So what the ANOVA box tells us is whether our model is significant. And then the coefficients box underneath that tells us what in our model is significant. If our ANOVA box is non-significant, we do not move forward in interpreting what's in the coefficients box. We just move on and say there is no significant prediction between diet quality and depressive symptoms. In this case, there is a significant relationship in the model, or there is a significant prediction in the model. So we move down to our coefficients box, which tells us what in the model is significant. And this is more helpful when we do our hierarchical regression, because in this box, we will have all of our predictor variables and our covariating factors, and we can see what in the model is significantly predicting depressive symptoms and how that impacts the relationship between diet quality and depressive symptoms. So here we can see that our t-value for our coefficient is -5.09 and our significance value is less than 0.001. So diet quality does have a significant prediction of depressive symptoms. This box also can tell us what the relationship looks like or what the prediction looks like. So our unstandardized beta tells us that as diet quality increases by 1 unit, depressive symptoms will decrease by 0.23 units. And that will just all depend on how the scores are measured. So as diet quality increases by 1 unit or 1 score, depressive symptoms will decrease by 0.23 units or 0.23 of a score. Now that's all in raw units. Over here at the standardized coefficients beta, which is 0.275, that one is standardized using Z-scores. Now this is not that important when there's only one predictor, but when we have multiple predictors, all measured in different ways, so age is in years, gender is in categories, dietary screening tool is a score between 0 and 105, they're all being measured on different scales. So the raw scores won't mean anything comparing each other, but the standardized scores are all Z-score standardized, so all of their scores are comparable. So the standardized coefficient becomes really important when you're looking at those covariates and those controlling variables later on. But for now, we know there is a significant prediction of diet quality and depressive symptoms. As diet quality goes up, depressive symptoms goes down by 0.23. Then we have our residual statistics that tell us a little bit about whether or not our residuals are or our assumptions are met. As you can see here, this is the histogram of the depression residual scores, not the normality scores of the raw scores. This is the residuals. And as you can see here, it's positively skewed. And that is completely normal. Completely normal to see in depression scores. So we wouldn't tend to see a normal distribution in depression scores. But that could be a problem for our analysis. And in concert with the fact that the Durbin-Watson is looking a bit strange, we might want to bootstrap our data. And we'll do that when we do our hierarchical regression. Our PP plot is kind of snaking around the line, which is another indication of non-normality. And there's our scatter plot of our residuals. So it's not looking too bad. It's still, you can put linearity through there, you can put a linear line through, and the assumption of heteroscedasticity, you just don't want to see those dots forming a cone shape, which they're not. They're nice here, they're a nice cloud. So we have our assumption of homoscedasticity has been met. Any questions about linear regression before we go and we move into analyzing a multiple hierarchical regression with those covariates and controlling variables? Okay. So the final step, actually, I might bring back the slides really quickly because there is an important slide on how to build your regression model when you have covariates. So we'll just go down to that. Right. So now we're going to build a model with our variables that were significant in our correlation. Now, this is a question that I get asked the most after I've done a workshop like this, is how do I know what order to put my variables in? So we had age, we had gender, marital status, we had social connectedness, we had sleep quality, we had sunlight exposure. How do I know what order to put the variables into my blocks so that they make sense in the analysis? So the decision has to be made based on theory, from reading widely, your literature, your research questions, your hypotheses, and of course, your own logic. There is more than one way to do it. And sometimes when I run my blocks, I'll reverse them because the interpretation doesn't make sense the first way. And maybe that will happen in this one, and I can explain it to you in a little bit more detail. You group variables together that are similar. So I always put my demographic variables together and my lifestyle factors together. And I don't want to separate them. Don't group variables together in one block if they are very different. Like you wouldn't put marital status and sunlight exposure together because one's a demographic and one's a lifestyle factor. The least important predictors go first. So demographics always go first in the blocks. And the most important variable, which is diet quality, goes in the very last block by itself. So there's a very important reason for this, is because you are trying to find out what the unique relationship is between diet quality and depressive symptoms when you're controlling for all the other things in the blocks above it. So doing our simple linear regression, we already know that the relationship between diet quality and depressive symptoms was 0.275, which is a weak to moderate relationship before we add our controlling variables. So let's go and see what it looks like, what the relationship between diet quality and depressive symptoms looks like when we control for all of those other variables. To do so, we want to go back to analyze, regression, linear, and then we want to reset what we had so that we don't have any of the old stuff in there. And we want to build our model again. So our dependent variable is depressive symptoms. So we put that in the dependent outcome box. And then when we build our model, who can tell me what demographic variables were significant in our correlation? I can go back through our chat to find out. So I think it was just marital status and education level. So in block 1, our least important variables are our demographics. So we put them first. So marital status and education level. In a block together, that's our first model. Then our second model is our lifestyle factors. So the lifestyle factors that were significant in our correlation matrix were social connection, sleep quality, and sunlight exposure. So they're all in a block together because they're similar variables. And then the final block or the final model is our diet quality. So we can see the unique variance of diet quality after controlling for the demographic and the lifestyle factors, which was what our research question was. In statistics, we want to include our confidence intervals and our covariance matrix. So that'll give you the same sort of thing as the correlation matrix before. We want to see our R-squared change. So that's going to tell us that little piece of information where we found out that diet quality had about 7.6% variability in depressive symptoms. It's going to tell us how that changes across each block. We want our descriptives, our part and partial correlations, our collinearity diagnostics that will tell us whether or not our predictor variables or our covariating variables are too closely related to each other. We want our Durbin-Watson or our independence of residuals and our case-wise diagnostics. 2 outliers across 2 predictor variables that are at 3 standard deviations away from the mean or more. Continue. Then we want to plot our residuals. Versus our predicted outcome. And our residual histograms, normality plots, and partial plots, and then continue. Then here we want to save our Mahalanobis, our Cook's distance, and our standardized predicted and standardized residual values. And this will tell us a little bit about outliers as well across our data set and whether or not we need to bootstrap. Options at 0.05, that's fine. And then because in our simple linear regression, we found that the residuals for the depression scale were a little bit non-normal and our Durbin and Watson was looking non-normal, I would bootstrap this regression. So perform bootstrapping at 1,000 samples, bias corrected accelerator, continue. And that will just adjust for those assumptions not being met. And it gives you a more, it's an adjusted model so that it's more sensitive, basically. And then we click OK. Now, one of the things that I do wrong every time I do regression and every time I teach regression, except for now, is I forget that all the assumptions testing is at the bottom of the output. So I'm not going to forget that today, and I'm actually going to go and check the regression assumptions first. So try and make a note to yourself. But after 7 or 8 years of doing this, I still forget every time. And I go and interpret my regression and get all excited. And then I get down the bottom. Why is it doing this? Oh,
Megan, there's a comment from Matt there about does bootstrapping extrapolate the current data to a much larger N?
yeah, it does. So it just creates 1,000, and it sounds like it's actually making it worse, but it creates 1,000 new sets of data from your data set, and it runs the data 1,000 times and then creates. So it adjusts and it's more sensitive. Last workshop, I sent around a video on bootstrapping, Alison.
That's
so we
right.
might also want to resend that video
Okay.
again to understand what bootstrapping does and is. Now something's happened to my output. Oh, that's why. I'm going to run it again. Okay. Luckily, SPSS always remembers what you put in. So if you need to run it again, I'm wondering if the bootstrapping is doing something weird to it. Let's run it without the bootstrap for now and just see what happens. And then we can run the bootstrap. Okay. Well, that's better. Okay. Right. So again, I'm not going to forget about my assumptions testing. I'm going to scroll all the way down beyond the regression assumptions and have a look. So what's interesting, and lucky we didn't bootstrap, because when we add the co-varying factors to the models, the scale of depression residuals are now normal. Interesting. Very cool. And the PP plot has corrected, so it's all nicely on that line. And the scatter plot looks a little bit different. Very, very interesting. Although that kind of looks like it might not be heteroscedastic. It's kind of a funnel. It's a weird shape. Interesting. And here we have our partial regression plots. And it's looking like that one's split into kind of like two, which probably is those with no depressive symptoms and those without, with marital status. Interesting. Okay, so looking at our residuals, I don't think we have a problem, and we may not need to bootstrap now. So that's good. So let's go all the way up to the top of the regression and analyze our multiple regression. Again, here are our descriptive statistics, with our mean at around 14 for depressive symptoms under that depressive symptom cutoff. And then the categorical variables won't really make sense too much in your descriptive statistics. We're not really interested in anything but diet quality and depression there. Then we have our correlation matrix again, which will tell us the same thing as what the one told us before about significance of the variables. Then our variables enter and removed box tells us what is in each model. So education level and marital status are in model 1. Sunlight exposure, sleep quality, and social connectedness are in model 2. And then the dietary screening tool or the diet quality score is by itself in model 3. So we can see the unique variance of diet on depressive symptoms after controlling for the demographic and the lifestyle factors. Here's our model summary. So down the bottom, it tells us in the notes, again, what is in each model. So model 1 with our demographic factors, model 2 with our lifestyle factors, and model 3 with diet quality. So our R squared for the demographic factors is 0.53. So if we take our R squared and we times that by 100, how much variability does marital status and education level have in our depressive symptoms? 5.3%. Good. Yeah, that shape was weird, but like a sausage almost. I'd have to go in and have a look. Thank you, Alison. Alison's put up the bootstrapping video, so take a watch of that. That will be able to explain bootstrapping in a better way than I could before. It's a bit of a complex topic of why SPSS creates new data to actually make it more stringent. Right, so let's have a look at model 2. When we enter the lifestyle factors, sunlight exposure, social connectedness, and sleep quality, and we times 0.604 by 100, how much variability do the lifestyle factors have with depressive symptoms? So 0.604 is the R squared value for model 2 with the lifestyle factors, times that by 100. What percentage of variability do the lifestyle factors have with depressive symptoms in model 2? That R squared there. 60%. Excellent. So that's very interesting. Something happened when we put those lifestyle factors in. And then when we add depressive symptoms, 0.608, how much variability is there with diet quality? .8. So it's added very little to the model. And you can see this over here in the R squared change column. The first R squared is 0.053 for the demographic factors. Adding lifestyle factors has increased the variability by 55%. And then finally in model 3, when we add diet quality, it's only added 0.03% or 0.3%. to the R squared change in the model. Now let's go and have a look at our Durbin-Watson. Our Durbin-Watson is now 1.468. So now we don't have a problem with independence of errors assumptions either. So doing a simple linear regression wasn't a very good model, but creating a multiple hierarchical regression is a much better model when looking at the prediction of diet quality and depressive symptoms. Yes, they are added together, the adjusted, well, the R squared. Very good. All right, so that is our interpretation of our strength and our direction of our relationships. But we don't really know what happened there with the lifestyle factors because we've got sleep quality, social connection, and sunlight exposure all together in the model. So we don't know which one of those is creating that big jump, that 55% jump in variability and depression. So the next most important box is our ANOVA box. Our ANOVA box tells us whether the model is significant. Now here we can see model 1 with our demographic variables is less than 0.001, which is significant. Model 2, including our lifestyle factors, is also less than 0.05, so it's significant. And including diet quality into the model in model 3 means that the model 3 is also significant. So this is really important, because if model 1 and model 2 were significant, but model 3 was not significant, that would indicate that after controlling for demographic and lifestyle factors, diet quality no longer has a significant prediction of depression, and that it was all involved with the other demographic and lifestyle factors. But because all 3 models are significant here, we know that the third model with diet quality and all the other variables is significant. So when we move down to the coefficients box, we only interpret the third model with everything in it. So this third model here at the bottom is the only model we now interpret to see what in the model is significant. Oh, Matt, thank you. Sometimes I get worried that I'm losing people. So the most important thing, the ANOVA box, whether the model is significant, and the coefficients box, what in the model is significant. If the third model is significant, we only need to interpret the coefficients box for the third model. We don't need to worry about model 1 and model 2. So here in the coefficients box, we want to go all the way over to the significance column and see, after we control for all the variables, what is still significant in our model. Who can tell me whether or not marital status is significant in our model once we control for all the other variables? We're looking at this column, the SIG column in model 3. Not significant. Good. What about education level? Is it significant? No. Good. What about social connection? Is it significant? Yes. Very. Remember, there is no very significant. You're either significant or you're not significant. It's a dichotomy, unfortunately. What about sleep quality? Yes. What about sunlight exposure? No. What about diet quality? No. Right. So once we add all of the variables into the model, only social connection and sleep quality are significant. And when we go over and have a look at the standardized coefficients box, so the third box from the left, it tells us that social connectedness, as social connectedness goes up by 1 unit, depressive symptoms goes down by 0.29. And as sleep quality goes, well, the sleep quality scores, if you have a read, because it doesn't make sense because it's positive, a positive relationship, right? Because there's no negative sign in front of that beta. Sleep quality scale scores range between 0 and 84. Higher scores indicate greater sleep problems. So as sleep problems go up, depressive symptoms go up. So this is why it's so important to understand your variables, because we could have easily gone, as sleep quality goes up, depressive symptoms goes up. That doesn't make sense. But it's because the sleep quality score is higher scores indicate greater sleep problems. So as sleep problems go up, depressive symptoms go up. And as sleep problems go up by 1, depressive symptoms go up by 0.5, so almost half. Good. Now, I know we're running out of time. We've got 7 minutes to go, but really quickly, what I want to explain to you, and I knew that this was going to happen because this happened when I did the live data set. Diet quality lost its variability in model 3, but the model was still significant. So I was wondering why that happened. So what I did in this circumstance, when I lost my variability of dietary screening, was I flipped the models. So I did model 1, dietary screening tool, model 2, demographics, and then model 3, I added the lifestyle factors, so that when I interpreted the model in my discussion, I could say diet quality was a significant predictor of depressive symptoms in the first model, but when we added social connection and sleep quality, diet quality was no longer a significant predictor. And then what would happen next, if you ever see this pattern in your data where your predictor no longer is significant, you can then run mediation with social connection and sleep quality to see whether they're mediating that relationship, which is what we'll do next week. Yes, Alan. Alan has a question.
Thanks. So I just want to check my understanding with the hierarchical model. You use theoretical and say some hypotheticals to choose which variables go into groups and order them. Is that correct?
Yeah. So in this example, and what I always do, because I know my variables from the literature, is I always put my demographics first because they're the least important, and then the lifestyle factors second, and then the diet quality third, or the predictor third, to see the unique variance. But when something like this happens, I flip it upside down just to see whether diet quality is still a significant predictor in model 1 if it was put first. So yeah, it's all based on logic and hypotheses, and all of this should be written into a pre-registration before you even collect your data. Or your modeling of how you're going to do your model in your regression should be done a priori, because it would be very easy and very improper for researchers to find something and change the way the model is built to meet their hypotheses. And that's called hypothesizing after the question, and it's very bad.
Statistical fishing expeditions.
Yeah. And just seeing lots of people like all of this what you're doing in the correlation matrix, and that you're only using the significant variables in your models and things like that, should all be written very clearly in a pre-registration document in Open Sciences framework. Definitely.
Thank you.
No worries. You have all done very well holding on today. If you have any questions for me at any time, feel free to, and these are just the slides that you can go through. I will send the PowerPoints with, Alison will give you the PowerPoints. So the PowerPoints go through each of the steps when you're clicking into SPSS as well. If you want to follow the video, follow the PowerPoints when you're doing your own analyses. And next week we will cover logistic regression, where we dichotomize that depression value between those who are and those who aren't above that score of 16. Then we're going to look at ANOVA. We're going to look at the different types of plant-based dietary followers and their depressive symptoms. So pescatarians versus flexitarians versus the vegan and then the vegetarians. And then I'll show you mediation and moderation in JAS, where we'll look at the social connection and sleep quality and what actually happened there with the diet quality and the depressive symptoms variables. So if you have any questions, feel free to email me. Follow me on my socials, where I do lots of fun food and mood stuff, and also lots of fun statistic stuff.
Thank you, everyone. Thanks so much, Megan. Very, very helpful. Some positive comments. Excellent. So hope to see you all next Thursday, 9th of May, for our final session on statistics with Dr. Megan Lee.